Okay, let's look at another problem here. This time we've got a g of s is equal to 100 times s plus 1 over s squared plus 110s plus 1000. Okay, so remember the first thing that we always do when we look at these is factor them into free s's, first order and second order systems. So this one actually can be factored into an s plus 1, and then our denominator can be factored into an s plus 10 and an s plus 100. Okay, so now we've got a pole, two poles, and one zero, and a gain. And so next thing we want to do is calculate the DC gain on this. So our DC gain is going to take all the s's equal to 0, excluding our free s's. So we've got 100 times 1 divided by 10 times 100. And what we end up with then is 1 over 10 equal 0.1. And moving that into dB, we end up with 20 log of 0.1, which ends up being minus 20 dB. Okay, so that's where we're going to start our plot, is at the omega equal 1 and the minus 20 dB. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. And let's start here with 0, 20, 40, minus 20, minus 40. And we're going to go up to the 1, minus 20. We're going to have a point there. That's going to be our initial point. Okay, our initial slope, we have no free s's, and so our initial slope is going to be horizontal. So we're going horizontal from negative infinity to our first pole, which is at 1. Okay, so the same point that we were at, and we see actually it's a 0, and so it's a 0. So remember our rule about a 0. When we have a 0, it's going to change the slope by a positive 20 dB per decade. And so we're going to start zooming up here at 20 dB per decade, and we're going to go till we hit the next pole, or 0, which is at 10. So it's right there, and then that is a pole, so we're going to have a change of negative 20 dB per decade. So we're going to move straight across from there to our next pole, or 0, which is 100 at this case. And so from 100, we've got another pole, so we're going to negative 20 dB per decade from our current slope. And so we're going to end up going down here like this. And that is going to be our magnitude plot for our Bode, asymptotic Bode plot. Okay, so now we want to start thinking about the phase, and the phase is going to be, of course, we've got the slope. The phase is equal to the slope times 90 degrees per 20 dB per decade. dB per decade. Okay, so our first slope is 0, so we're going to end up with a 0 slope, and then we're going to have a positive 20 slope, and so that's going to end up with a positive 90. That's going to yield a 90 degree phase shift, and then we're going to go back to a 0, and then we're going to go to a negative 20 dB per decade, which is going to result in a minus 90 degrees. Okay, so if we start looking at that, 0, 90, minus 90, we're going to end up 0 from here to here, and we're going to end up with a positive 90 from here to here, and then we're going to end up with a 0 again from here to here, and then a negative 90 for the rest of the way out. Okay, so this is what our asymptotic Bode looks like. Again, we want to look at stepping back 1 decade and forward 1 decade. So this transition would happen over here. This transition would happen through this range. This transition would happen through this range, and we get some a bit of funkiness going on here. But what is going to happen is we're going to move kind of through those and around them. We'll kind of squint our eyes a little bit, and it's going to look something like that. Okay. So that is our asymptotic Bode for that transfer function. And again, what I want to make sure you start thinking about is the idea of our gain being able to shift the plot up and down, okay, and our zeros will move the plot up, and our poles move the plot down. So we're going to use these poles, zeros, and gains to reshape our controller poles, these zeros and gains, to reshape the Bode to a desired shape that will give us the best performance. And this is called loop shaping. That's where we're headed with all this, is ultimately to the design. Okay.